Hey everyone, I hope you had a good time so far at this conference, and welcome to the last and final talk about a kernel RCE for the PlayStation 4, which is probably the closest to hacking ROMs. So my name is Andy. You may also know me as The Flow, and I'm a security researcher who focuses on low-level security. And over the past decade, I have been doing lots of PlayStation console research during my free time. Before we dive into the RCE, I will give you a brief context about the PlayStation operating system and its security on both the PlayStation 4 and the 5. So the PlayStation 4 has an AMD Jaguar, and it runs the FreeBSD 9 kernel, whereas the PS5 has an AMD Zen 2 CPU, and it runs the FreeBSD 11 kernel. The kernel has lots of modifications from Sony, so they added lots of custom syscalls and drivers for their peripherals, and they're all closed source. And in the table below, you can see the most important mitigations. The PS5 has lots of modern mitigations such as the CFI or execute-only memory, and of course also SMAP and SMAP, and also KSLR. The PS4, on the other hand, as you can see, lacks all of these mitigations except KSLR. And in later slides, you will see how the lack of these mitigations makes exploitation on the PS4 much easier. So let's talk a bit about the past vulnerabilities that I have found. Since a lot of code from FreeBSD is left untouched, you can also look at upstream bugs and see if they affect the PlayStation. And Sony usually only backports patches for which there are advisories or CVEs. And sometimes there are commits which are fixing vulnerabilities that do not have advisories. So if you want to earn some pocket money on HackerOne, just browse through the commits and see what has been fixed in FreeBSD. So in 2019, I found the following zero-day. It's a use after free vulnerability that lies in the packet options command of the setsocopt syscall. So the issue here is that the command doesn't have any locking mechanism, and it calls into a function that operates on the global packet options. And this function namely stores the the packet options locally on the stack or in some register, and then the pointer is set to 0. If no options are provided, then the handler turns off the options and frees the object. And otherwise, the previous options are updated with the newly provided options, and the pointer is written back. And the issue here is very easy to see. Because there's no locking, two threads may call into the same function at the same time and dereference the same pointer. And so if one of the threads clears the options while the other uses the options, we may end up with a race condition use after free. And this vulnerability is quite powerful because there are lots of primitives on the packet options. And similar to the sock puppet exploit by Ned Williamson for iOS, this can be easily exploited to get arbitrary read and write primitives. Instead of auditing the FreeBSD source code, we can also reverse engineer the kernel binary and search for custom code by PlayStation. I grew up hacking the PlayStation handhelds, and I found tons of bugs there. So I knew there was a great chance to also find bugs on the PS4 in the custom code, especially because they are usually shared and used across different platforms. So for example, Sony added this custom driver for the exFAT file system. And there I found a heap buffer overflow that was triggerable by just plugging in a malicious USB drive. In this code here, there's a function that creates a heap allocation, and it uses a 32-bit size. And there's another function that reads in the upcase table from the exFAT file system. So namely, it reads a 64-bit field, and it passes it to the create heap function. And so that's basically a size t to int truncation. So if you provide a size that is bigger than 4 billion, you may end up with a small allocation only. And the subroutine then reads in the upcase table sector by sector, and at some point it will overflow and corrupt adjacent objects. And this vulnerability is also super simple to exploit because you can choose in which zone the to allocate the data and also how much you want to overflow. So all the kernel exploits on the PS4 more or less follow the same procedure. So first, they corrupt a kernel function pointer to redirect to a ROP chain that is based in the user space, which is possible because, as mentioned earlier, there's no SMAP and SMAP. And then they defeat KSLR. And nowadays, it's usually the other way around, where you need to defeat KSLR first, and then you get rip control. But here, you get rip control, and then you defeat KSLR, which is quite trivial, because there's still some registers in that point to some data segments or text segments. So you can just dynamically resolve the kernel base address. And next, what we do is we disable the write protection using dynamically resolved gadget that writes to CR0. And with that, we are now able to modify the kernel code to add some patches, for example, in order to enable all the permissions. We enable the JIT capabilities, and we also install a fake syscall, which is called kexec, and that does nothing else than just jumping to the first argument in kernel context. So with that, we can just map a payload in user space with the JIT capabilities and use the kexec syscall to jump to it. All the previous kernel exploits so far were chained with some user space exploit. So usual entry points are WebKit, BDJ, or some safe data vulnerability. For WebKit, bugs are usually taken from Project Zero to gain read and write primitives in the browser. They are usually simple to exploit and also simple to use for end users. But the WebKit exploit process is heavily sandboxed, and it doesn't support JIT. So also here, we can't use all the bugs from Project Zero, only those that do not rely on JIT. BDJ, or Blu-ray Disk Java, is something that I researched a few years ago. I found that if you manage to escape the Java sandbox, you basically get native code execution for free. And this attack vector is quite promising, as it is firmware agnostic, and the BDJ process is much more privileged. So for example, it also supports JIT. Downsides are that you require a Blu-ray disk burner, of course, and the disk drive is something that is commonly broken on the PS4, so not everyone can use this exploit. And all the ways I found to escape the Java sandbox have been patched on the latest versions, but maybe there are still some JVM bugs that you can exploit to break out of the sandbox. And finally, for safe data exploits, the biggest advantage is that some are unpatchable, because you can just buy the physical disks and decide not to install the updates. The downsides here are that you require an already hacked console in order to install the safe data files. And CTURT, Chris Ertl, also did some research on a slightly different attack surface. Namely, he found ways to hack PS2 games and also escape the PS2 emulator, which has similar privileges as BDJ. So my goal in security research is always to explore and find various ways to break a system. And I always dreamt about a kernel, about a remote exploit for the PS4. Some remote attack surfaces that I looked at were in Bluetooth, remote play, and the TCP IP stack. Bluetooth only has some minor bugs, and I couldn't find a way to do some memory corruption or similar things. And compared to the Bluetooth subsystem of Linux, I found that it was surprisingly more secure. So for example, on Linux, I was able to do an RCE, which is called Bleeding Tooth, that I released a few years ago. The remote play functionality is something that can only be used on the latest versions. So an exploit there wouldn't be interesting because no one would be able to use it once it's patched. And for the TCP IP stack, there are some advisories for FreeBSD, but unfortunately, they are not applicable or exploitable on the PS4. So what else is there? Looking deeper into the kernel binary, I found some interesting strings. Some that caught my eyes were the following file names: IF PPPoE and IF as PPP sub R. And those are not available in FreeBSD. And searching on Google, I found that it was in fact code from NetBSD that they merged. PPPoE is something that a user can choose when setting up the internet connection on the PS4. But what exactly is it? The name stands for point-to-point protocol over Ethernet, where they basically encapsulate PPP frames inside of Ethernet frames. And it is used to provide internet access over DSL, and it provides authentication, encryption, and compression. So how does the protocol work? Let's have a look at the following diagram, where a PPPoE client, which is the PS4, communicates with a PPPoE server, here like a modem or our computer. And we see that the protocol has 3 stages. The first is called the discovery stage, where the client broadcasts a party initiation packet. And the server listens for that packet and replies with a PATO offer packet. And then they send a few more packets back and forth to complete the handshake. The second stage is called the session stage, where they use the link and IP control protocols to negotiate configurations such as the maximum receive units or authentication methods, or also setting the IP addresses for the client. And then it's basically ready to transmit data, and the TCP/IP stack can be used on top of PPP. And then the final stage is called the termination stage, where everything is destroyed upon a PAT-T packet, which can be sent by both the client and the server. All right, so let's dive into the vulnerabilities that I have found in this protocol. So I started by reverse engineering the PS4 code, as I wanted to understand if it was just the plain code from NetBSD, or if they added some modifications. So just after 5 minutes, I found a bug in the link control protocol. Namely, this function here parses the LCP packet, and it is encoded with the TLV format, which consists of a type, a length of the value, and then the value itself. And what's special here is that it sends back all the invalid options to the server. And for that, it allocates a buffer R for rejected options, where the length is controllable. And then it goes through the TLV stream, and for every byte that is unknown, it adds it to the rejected list. So the problem here is that it just copies the TLV entry with an arbitrary 8-bit length, without even checking that the buffer is actually big enough. And then it sends back all the rejected options to the server, as you can see. So it's a simple and classic heap buffer overflow. And I was super happy because I thought I found a 0-day in BSD, and I could get a new CVE for this year. But I was actually looking at the PS4 code in IDA. And when I looked at the upstream code, however, I saw that the bug was actually fixed already. And it was fixed a long time ago, in 2006. And somebody joked and said that this CVE is even old enough to drive a car. So when I ran some experiments to trigger the bug, I noticed something strange. So this is the packet that contains the rejected options. What caught my eyes is that there are some strings which look super similar to a pointer. But that shouldn't be the case, because this is the mbuff cluster zone, which is segregated from the rest of the heap. And it should only contain socket and network data. So there's no way it can contain any structures or even pointers from the kernel. So what's going on? So it turns out that the kernel pointer is actually sent over the network by design, and it's coming from the PS4. And looking at the packet received in SCAPI, we can see that there exists a PPPoE tag in the tag list called host unique, which basically has a kernel pointer as a unique identifier of the client. And that's an address to the PPPoE interface object, which is a super nice idea, right? And looking at the upstream code again, I found that the information leak was already patched in 2018. However, they didn't create an advisory for it, and that's why the PS4 was still vulnerable. So what's the potential of this information leak? The pointer that we leaked is located on the heap, so it cannot be used to defeat KSLR. But it may still be very practical for exploitation, as it's a pointer to the following structure, as mentioned before, called PPPoE softc. And some interesting fields here are the ASCII list, which is pointer to a data segment. There is a SC_dest and SC_session, which is the MAC address and the session ID, and both are attacker controllable. And finally, we have the SC_AC cookie and the SC_relay SID, which are pointers to controllable buffers. So there's a lot of useful stuff here. If we have an arbitrary read, we can just leak this pointer, this structure, and read the data segment pointer. If we need to plant some data at the known address, we can use the MAC address and the session ID and plant 8 bytes of controllable data. And if we need a pointer to some controllable buffer, we can use the AC cookie and the relay SID. And in our exploit, we will make use of all of these fields. So at the beginning of the protocol, when getting a PuTTY initiation packet from the PS4, we have an information leak. And when we finish with the discovery stage, we can send a LCP configure request to trigger memory corruption. Both of these bugs are super easy to trigger, but how can we combine them and exploit them? What we still need is a good target that we can corrupt that may allow us to gain arbitrary read and write or even RIP control. And for that, we have to look for some structures that are allocated using malloc in the network stack or some similar functions. And we also need a KSLR bypass in order to build ROP chains and so on. And for that, we can maybe find more bugs or otherwise corrupt something that would allow us to leak the PPPoE soft C instance. So that's the same goal as the previous one. So find a nice structure that we can corrupt. So if it's a complicated enough structure that allows us to leak information, we probably can also get RIP control with it. So let's get to everyone's favorite topic, ASLR. So KSLR for local privilege escalation exploits is super simple to bypass because there are various ways you can allocate interesting structures where buffers are copied in or out from the kernel. So for example, I pioneered the method to leak memory by corrupting the message structure on Linux, which also works with any heap primitives, such as heap use after freeze or heap buffer overflows. And there are also many CPU side channel attacks available that allow an attacker to break KSLR. So for example, via prefetching or BTP collisions. ASLR for remote attacks, however, is a different story. In our case, we are not attacking an Android messaging app, which just responds with the same address space and where we can build an oracle to defeat KSLR bit by bit, or even brute force the whole way through. In our case for the kernel, a wrong guess would result in a reboot of the system, and that would take several minutes. So therefore, in this research project, I mainly focused on achieving a reliable KSLR bypass as a remote attacker, which actually took me a whole month. So the plan is to use our heap buffer overflow in order to corrupt some states in the network stack that will make the kernel send us back some information, ideally something that contains some pointers. And in order to do so, we can just go through all the malloc invocations or similar functions. So the first potential object we find looking for malloc is in the IPv6 fragmentation code. As you all know, you can send an IP packet consisting of multiple fragments, which may also arrive out of order. So therefore, there needs to be some internal list in the kernel that keeps track of these fragments and their corresponding offsets and lengths. So the idea is to send a bunch of ICMP echo requests with lots of fragments. And then we trigger the corruption and override an AmpBuff pointer to point to somewhere else. So as mentioned earlier, the AmpBuff, which is similar to skbuff on Linux, is in a dedicated heap zone for network data. And finally, we receive all the ICMP echo replies. But for the AmpBuff that we corrupted, we should expect to receive something else. Here, in our case, some information leak. So here are the objects that are allocated for a fragment. There are fields for the fragment offset, for the length, etc. And there's also an AMP-buff containing the fragments data. And as you can see, it's implemented as a doubly linked list, where there are pointers to the previous and the next fragments. And that's actually a big issue for us, because we only have a linear buffer overflow. So therefore, in order to control the AMP-buff, which is located in the middle of this structure, we would also need to corrupt the up and down pointers, and also provide valid pointers for them. So I couldn't find a way to achieve this, because all I could do was planting 8 bytes of controllable data at a known address, which was not enough to create a valid fragment structure. So I ditched this idea and looked further. The second thing we find looking for malloc invocations in the network stack is the IPv6 neighbor discovery code. So the IPv6 neighbor discovery protocol is very similar to the ARP protocol for IPv4. And it is used to determine the MAC addresses of the IPv6 hosts on the same network. And this protocol is also used in order to determine if nodes are still reachable or not. And here, very important, a request is called solicitation, and a reply is called an advertisement. So these terms will be super relevant for the following slides. And as indicated, there's a cache of IPv6 hosts with their corresponding MAC addresses. And that must be allocated and stored somewhere. So what surprised me is that there was no size limit of that cache. So an attacker can just allocate a bunch of these entries using different IP addresses. So that's basically what we do. We can mount a flooding attack and add a lot of entries to the neighbor cache, which is also our heap spray. So the computer can just say, hey, I am this address, hey, I am that address, and the console will store all of them in the linked list. And in FreeBSD, the neighbor cache is implemented with a hash list that is indexed with 6 bytes of the IP address. So here, in our case, we just use for one for one in order to let the entries be in the same doubly linked list. If you look at how the IPv6 neighbor discovery protocol works, you can find that there's a well-defined state machine underneath. So the following diagram shows that each entry in the neighbor cache can have 5 different states, where some of them, for example, the incomplete state contains a loop that is called retry NS for retry neighbor solicitation, so requesting the MAC address of the peer. So when a node on the local network receives a packet from a different node, for which there's no entry of the IP address or the MAC address yet, it sends this neighbor solicitation packet to request the MAC address. And when the peer receives the neighbor solicitation packet, it will reply with a neighbor advertisement packet with its own MAC address. So once the other node gets the response, it will go to the reachable state, and which has a TTL of 24 hours. An interesting observation here is that before it knows the MAC address of the peer, it will hold back all the outgoing packets. So for example, if you send an ICMP echo request with an unknown IP address, you will not get a response back until you send a neighbor advertisement packet with your MAC address. So the second attempt to defeat KSLR exploits this behavior. The idea is we send many packets with different IPv6 source addresses, and that will trigger a lot of allocations of LL entry objects on the target machine, on the PS4. Here, LL entry stands for link level entry, and that's basically an item in the neighbor cache. And then we receive lots of solicitation messages from the target machine, because it doesn't know any of those IP addresses. And we reply to all of them with advertisement packets in order to keep the entries in the reachable state. So they will have a TTL of 24 hours and stay in the hash list. And once they are stored safely in the cache, we trigger the corruption and overwrite one LL entry object. And what we do is we change the reachability state from reachable back to incomplete. And we also store a fake AMP-buff that will be later sent out. And finally, we send IPv6 neighbor advertisement packets for all the different addresses. And for none of them, we should actually get a reply, because they are already in the reachable state. But for the one LL entry where we change the reachability state, we should expect something else. So for that, we should expect to receive an invalid packet that contains leaked data after the IP header. Let's take a look at the neighbor advertisement input handler. It does a lookup of the IP address, and at some point it checks if the field LA hold is non-empty. And that's the field that stores all the packets that should be sent only once the neighbor advertisement packet is received, in which case the function anti6 output LLE is called. So the idea is to hijack this pointer so that it sends out a different AMP-buff. So this method worked quite well when testing, and I was able to leak memory and also defeat KSLR. But the big problem of this approach is that the AMP-buff is freed after sending. And that's super annoying, because if we want to leak the PPPoE softc instance, we will also corrupt it when we free it. And if it's corrupted, we cannot use it for some further exploitation. Looking at the LL entry structure more closely, we can see there are many interesting fields. To show you the fields from the previous attack, here is the LN state, which is the reachability state. The field LA hold is the linked list of held back packets. And before that, there's one interesting pointer of the type LL table. And that structure contains some more interesting fields, such as the IFP, which is the pointer to the interface object, and also a function pointer that is called to free the LL entry, for example, when it is no longer reachable. And here is how the neighbor's discovery state machine looks like underneath. As mentioned before, when the state is incomplete, it will send out the neighbor solicitation packets for a few times. And here we can see that the interface object pointer is retrieved from the LL entry, and then it is passed to the anti6 NS output function. So because we can corrupt the LL entry, we can also control the interface pointer. And in the neighbor solicitation output handler, we can see that when asking for the MAC address of the peer, it will actually also say, hey, that is my MAC address, basically. And this MAC address is received from the IFP, from the interface, and it is copied into the output handler. So this looks like a fantastic way to leak information. If we are able to corrupt the IFP pointer, we can make it retrieve the MAC address from somewhere else. And this object is not freed after sending, so we can still use it after leaking. So the final KSLR bypass is the following. We send many packets with different IPv6 source addresses, which will allocate a bunch of LL entry objects on the target machine, as before. And then we receive lots of these solicitation packets, because none of these IP addresses exist in the cache yet. And similar to the previous approach, we reply to all of these requests with advertisement packets. And now we corrupt the LL entry of one cache entry, and we change the reachability state also back to incomplete. And we also corrupt the IFP pointer, the interface pointer. And next, we send ICMP echo requests for all the different addresses. And for all the addresses which have not been corrupted yet, we should receive an ICMP echo reply. But for the LL entry that we corrupted, we should receive an IPv6 neighbor solicitation packet. That's because we modified the state from reachable to incomplete. And so this packet should now contain leaked data as the MAC address. So let's take a look at the KSLR defeat visually. We have three components here. On the left-hand side, we have the corrupted LL entry object. In the middle, we have the PPPoE softc instance for which we know the address. And on the right side, we have the fake object. Here we planned a fake IFNet object. So when we corrupt the LL entry, we redirect the LLE table pointer to the PPPoE softC object. And it is located in such a way that the IFP, the interface pointer, is aligned with the ASCII AC cookie. And that's the pointer to our fully controllable buffer. That buffer represents the fake IFNet object, where the IF address, which is the MAC address, is pointing back to the ASCII test and ASCII session. And these are the fields where we can plant some controllable data. And here we just plant a pointer to itself so that we can leak the ASCII list. And yeah, with that, by abusing various fields of this object, we can finally leak a data segment pointer. And with that, we can defeat KSLR, as you can see in the logs. So we trigger the memory corruption. We scan for the corrupted LL entry object by checking the replies of ICMP echo requests. And for the corrupted one, we should expect to receive a neighbor solicitation packet. And then we can decode the packet and find the data pointer as the MAC address. And with that, we calculate the KSLR offset. And that was a great moment, because I could finally start writing the ROP chain. So to get RIP control and also ROP chain code execution, let's take a look at this diagram. It's a bit complicated, so please bear with me. So again, on the left-hand side, we have the corrupted LL entry. It's the same entry that we corrupted before for the KSLR defeat. In the middle, we also have the PPPoE softC instance, which is also the same as before. But now we redo the negotiation in order to set a different MAC address and also different session ID in order to plant some other pointer. And we also choose a different AC cookie. So now we build a fake LL entry object on the right-hand side, which now takes the KSLR offset into account. So the next pointer of the LL entry points to the PPPoE softC object. That next entry isn't a valid LL entry, but it doesn't matter, because the lookup method will just iterate through all the next pointers and until it finds one with a matching IP address. So in our case, it will go to the right object, which is basically the ASCII AC cookie. And yeah, therefore, we control the whole object. So in the fake LL entry object on the right side, we now point the LLE table pointer back to the PPPoE softC object. And that one is aligned in such a way where the free function pointer is aligned with our ROP gadget. So what happens when we when the LL entry is out of scope is that the free function is invoked, and as the second argument, it will take the LL entry. So in our case, it will take the fake object here on the right side. So we can just dereference from it. So what we do is, the second job gadget is that it saves the RBP register in order to restore the stack in the future. And then it jumps to the third job gadget, and the rest of the job chain basically does a stack pivot to a ROP chain, which is located at the end. So with that, we can now have ROP chain code execution. And we split the ROP chain into two parts. The first copies a secondary ROP chain to the original stack that we saved earlier, and then stack pivots there. And we do so because we want to invoke some functions in the ROP chain, and those shouldn't corrupt the fake stack, which is actually the heap in our case. And then the second ROP chain then disables the write protection, patches the kmem alloc function to enable the RWX protection. Then it restores the write protection again, allocates a executable page, and copies in the stage 1 payload, and then it can just jump to the stage 1 payload. But the stage 1 payload is limited in size, as it needs to be smaller than the MTU In our case, that's only 1,500 bytes. But that's more than enough for us, because we can just enable the UART. We can restore everything that has been corrupted. And then we create a new process that listens for the stage 2 payload. And that one can now be of any size. And finally, we restore the stack pointer and perform the epilogue of the timer function to ensure process continuation. And with that, everything is restored and everything is working correctly, as if nothing happened. There was supposed to be a video, but it's not too relevant. You can find it on YouTube as well, on Twitter. But the exploit works super well. And the community made a bunch of pull requests to add support for all the firmwares. It's especially interesting because the exploit can be triggered on boot, because the PlayStation makes some connection to the Sony servers. And yeah, it's fun to see that the Chinese people took over my work and created a jailbreak dongle, which they are selling for $30. That's it. Thanks for your attention.
Thank you, Andy. So we have a couple of questions from the audience. So the first one is a little provocative. How long until we can play backup games on PS5?
I actually haven't played any games. I only hacked the console for fun, and I didn't even do anything once I got like kernel rip control. Yeah.
Okay. Next question. I've always felt like the console hacking scene was something really hard to get into, mainly due to lack of resources. What are your suggestions to get started?
There are various write-ups available from CTURD, from Spectre, and all the. Yeah, I also have some write-ups for the PlayStation Vita, and also. No, I don't think I have anything for PS4, but I have some talks available. So I recommend reading them, watching the videos, and yeah.
Maybe you can share in a tweet.
Sorry?
Maybe we can share some resources in a tweet.
Yeah, I can do it.
All right. OK, thank you very much. Thank you, Andy.